Welcome back to Java Internals Crashcasts. I'm your host Sheila, and today we're diving deep into the HotSpot VM architecture. We're in the advanced topics season, specifically the JVM Internals chapter. Victor, are you ready to explore the inner workings of the HotSpot VM?
Absolutely, Sheila. I'm excited to unravel the mysteries of the HotSpot VM for our listeners. It's a fascinating topic that's crucial for understanding Java's performance.
Before we begin, listeners, you'll want to be familiar with basic JVM concepts and have a general understanding of how Java programs are executed. Now, let's start with a quiz question to get our gears turning. What percentage of the code in a typical Java application do you think gets JIT compiled by the HotSpot VM during runtime?
Oh, that's an intriguing question, Sheila. It really makes you think about how the HotSpot VM optimizes code execution. Without giving away the answer, I'd say it's a smaller percentage than most people might expect. The VM is quite selective about what it chooses to compile.
That's right, Victor. It's a crucial aspect of HotSpot's efficiency. Now, let's start with the basics. Can you give us an overview of what the HotSpot VM is and why it's called HotSpot?
Certainly. The HotSpot VM is the primary Java virtual machine implementation used today. It's called HotSpot because of its ability to identify hotspots in the code, portions that are executed frequently, and optimize them for better performance. Think of it like a city planner who identifies the busiest intersections and optimizes them for smoother traffic flow.
That's a great analogy. So, if the HotSpot VM is like a city, what would be its main districts or components?
Great question. The HotSpot VM has several key components. These include the class loader subsystem, runtime data areas like the heap and method area, the execution engine, the garbage collector, and the JIT compiler. Each of these districts has a specific role in running Java applications efficiently.
That's quite a complex system. Let's focus on the runtime data areas first. How does HotSpot manage memory, and why is this important?
HotSpot's memory management is crucial for performance. The heap is where objects are allocated, and it's divided into different generations for efficient garbage collection. The method area stores class structures and code. There's also a Java stack for each thread, and a PC, program counter register. Efficient memory management allows for faster object allocation and better use of system resources. It's like organizing a warehouse. Good organization leads to quicker retrieval and more efficient use of space.
I see. So, the heap is divided into generations. Can you explain a bit more about this generational approach?
Certainly. The heap is typically divided into 3 generations: young generation, old generation, and permanent generation, though this changed in later Java versions. The young generation is where most new objects are allocated. It's further divided into Eden space and 2 survivor spaces. The idea is that most objects die young, so we can collect garbage more efficiently by focusing on this area frequently. Objects that survive multiple garbage collections are promoted to the old generation. This area is collected less frequently, but more thoroughly. This generational approach is based on the observation that most objects have a short lifespan, allowing for more efficient memory management and faster application performance.
That's fascinating. It's like a city with different neighborhoods for new residents and long-term inhabitants. Now let's move on to the execution engine. How does it work with the JIT compiler?
Great analogy, Sheila. The execution engine is the heart of the HotSpot VM. It reads the bytecode and executes it. Initially, it interprets the bytecode, but here's where it gets interesting. It works closely with the JIT compiler to optimize frequently executed code. The JIT compiler identifies hot methods, those that are called frequently or contain loops. It then compiles these methods to native machine code for faster execution. This compiled code is stored in a special memory area called the code cache. It's like having a translator, interpreter, who learns to speak the local language, native code, for phrases they use often, making communication, execution, much faster over time.
That's a clever system, but doesn't compiling code at runtime introduce some overhead?
You're right to ask that, Sheila. JIT compilation does introduce some overhead, But HotSpot uses adaptive optimization to balance this. It starts by interpreting everything, then gradually compiles and optimizes the hotspots. The VM uses different levels of compilation. It might quickly compile a method with basic optimizations first, then later recompile it with more advanced optimizations if it remains hot. This approach ensures that compilation effort is spent where it will have the most impact on performance.
I see. So it's constantly analyzing and adjusting. Are there any other performance optimizations in the hotspot architecture we should know about?
Absolutely. HotSpot incorporates several other optimizations. For instance, there's Escape Analysis, which analyzes how objects are used and can sometimes allocate them on the stack instead of the heap, or even eliminate allocations entirely. There's also Inlining, where small methods are inserted directly into the calling method, reducing the overhead of method calls. Loop unrolling is another technique that can reduce the number of iterations and branch predictions. Lastly, there's lock coarsening and elision, which can optimize synchronization by combining adjacent synchronized blocks or removing unnecessary synchronization. These optimizations work together to squeeze out maximum performance from Java applications.
Wow, that's impressive. It seems like there's a lot going on behind the scenes. Now remember our quiz question about what percentage of code typically gets JIT compiled. Any guesses before we reveal the answer?
It's a tricky one. Based on what we've discussed about HotSpot's selective compilation, I'd guess it's lower than most people might think. But I'm curious to hear the actual number.
You're on the right track, Victor. The answer is, typically only about 3 to 10% of an application's code is JIT compiled. The exact percentage varies depending on the application, but it's usually a small fraction of the total code. This shows how efficient HotSpot is at identifying and optimizing the most critical parts of an application.
That's fascinating. It really demonstrates the power of focusing optimization efforts where they matter most.
Absolutely. To wrap up, let's summarize the key points about the HotSpot VM architecture. 1. It's designed to identify and optimize frequently executed code. 2. It uses a generational heap for efficient memory management. 3. The execution engine works with the JIT compiler to adaptively optimize hot code paths. 4. It employs various advanced optimization techniques like escape analysis and inlining. 5. Typically, only a small percentage of code, 3 to 10%, is JIT compiled, focusing on the most impactful optimizations. Victor, any final thoughts on the importance of understanding HotSpot's architecture?
Absolutely, Sheila. Understanding the HotSpot VM architecture is crucial for Java developers who want to write high-performance applications. It helps in making informed decisions about code structure, memory usage, and even in troubleshooting performance issues. The HotSpot VM's sophisticated optimizations allow Java to compete with and often outperform natively compiled languages in many scenarios.
Thank you, Victor, for these insights. Listeners, in our next episode, we'll be moving on to our new chapter on reactive programming, starting with an introduction to reactive streams. It's going to be an exciting shift in our exploration of advanced Java concepts. If you've enjoyed this deep dive into the HotSpot VM architecture, please subscribe to Java Internal's Crashcasts and leave us a rating. Your support helps us continue bringing you these in-depth explorations of Java's inner workings. Until next time, keep coding and stay curious.